Let's start with the equipotential surfaces. Equipotential refers to same potential. The surface which has got same potential all over the surface, it is called as an equipotential surface. Then it can be a physical surface or it can be an imaginary surface. If it is a real surface, mostly it is kind of like it is on the surface of a metal. It is the huge metallic body is there, and the outer surface of that metallic body will always remain at a same potential. So that surface can be referred to as an equipotential surface. Similarly, we can also have an imaginary surface, the Gaussian surface. That Gaussian surface can also be referred as an equipotential surface, because if we take the Gaussian surface at the same distance from a point charge or from a group of charges, if the distance remains same, in that case that surface can also be taken as an equipotential surface. So the surface can be physical on the surface of a metallic body, that is the surface of a metallic body, or alternatively it can also be an imaginary surface like a Gaussian surface. So the equipotential surfaces are those surfaces on which the potential remains same at all the points. So that is about the equipotential surface. Then there were four properties of the equipotential surfaces. First property was no work is done in moving a point charge on an equipotential surface. So if I'm trying to move a point charge over an equipotential surface, there will be no work done, and the proof was, let us say there are 2 points on the surface. Let's say there is a surface, there are 2 points A and B. We are trying to move the point charge from A to B. Then the WAB, that is the work done between A and B, will be equal to Q into B, and that B will be equal to, we can take it as VB minus VA, that is the final point minus the potential at the initial point. But we know that this is an equipotential surface, so VB will always be equal to VA. So Q will be multiplied with a 0. The resultant work done should be a 0. This is the first property of an equipotential surface. Then the second property was the electric field is always normal to the equipotential. So electric field is always normal to the it is always normal, or I can say perpendicular to the equipotential surface. So let us say there is a surface and the electric field should always be perpendicular to this equipotential surface. Now why this should be the case? Now why this should be the case? The answer for this question is, if the electric field was not normal, in that case this electric field will have 2 components. One will be perpendicular to the surface and one will be parallel to the surface. Let us say if the electric field was like this, there will be one component which is going to be parallel and one component which is going to be perpendicular. If we have this kind of components, this doesn't matter, but if there is a component along the surface, then it needs the work to be done to move a charge along the surface, which is practically not true because of this first property. Because what you have said in the first property is that to move a charge on the equipotential surface, the work should be 0. So if there is a component along the surface, work needs to be done, which is not true. Hence the electric field is always normal to the equipotential surface. So that was the second property. Then the third property is again similar to the property of the electric field lines, that is 2 equipotential surfaces never intersect each other. So if they intersect, that means the point of intersection will have two different values of potentials, and that is practically not possible. One point can take only one potential at a time. It cannot take two different values of potentials at the same time. So the two equipotential surfaces will never intersect each other. Then the fourth property was equipotential surfaces are closer in the region of strong electric field and further apart in the region of weak electric field. So wherever we are going to have the electric field to be strong, let us say I am going to take the example of a unit positive charge. If I am near to this charge where the field will be strong, then this will become my first equipotential surface. This can become my second equipotential surface. Then it goes third equipotential surface, fourth, fifth, sixth. So as I am going away, the equipotential surfaces will be going further apart. In the near region where the field is strong, the equipotential surfaces will be close to each other. But as I am going further away from the charge, then my electric field lines or the equipotential surfaces will move further away. Have the relation as E is equal to minus dV by dr, and for equipotential surface that dV term remains constant because we are talking of the same potential surface. We have only association between E is proportional to 1 by dr. If I want dr, this is going to be proportional to 1 by E. So this is the relationship. If the field is strong, then the distance between the two surfaces will be more. If the field is strong, distance will be less. If the field is weak, then the distance will be more. So that is the proof of the fourth property, that is the AND. If there were electric field lines passing along in the space, then if I draw a surface which is perpendicular to those lines, then this surface which is supposedly perpendicular, it will have the same potential all over. Talking of the equipotential surface of a single positive charge, they will be concentric circles. So these will be the equipotential surfaces for the single positive charge. Similarly, instead of having one positive charge, if I have two positive charges, then the equipotential surfaces near to the charge will be independent, but when the lines meet, they are going to be something like this, and further away they are going to join together. So for the equipotential surfaces for a pair of positive charges, they are going to look something like this. Then for the case of an electric dipole, it will contain one positive charge and one negative charge. We have one equipotential, we have got the second equipotential, we can have the third equipotential, and for this we are going to have one equipotential, second equipotential, third equipotential, but the line in the center will not have any potential. This line will always have a zero potential. The equatorial line which is passing through the origin or the center of the dipole, that line will always have zero potential. So these two lines never meet each other. These two pair of surfaces, equipotential surfaces, they never meet each other. They never intersect with each other. The positive potential remains independent. The negative potential also remains independent. They never meet, they never intersect. Only for the case when there are two positive charges, or for the matter as a consideration, if there were two negative charges also, in that case also the surfaces, equipotential surfaces, will have the same look or the same diagram.